In this video, we're going to look at how we can use linear combination of atomic orbital, or Lcao, to build molecular orbitals that can be used in the Schrödinger equation of molecular system of molecules, whether diatomic or polyatomic molecules. All right, let's get started with that. So the learning objective is to describe how molecular orbitals are expressed as linear combination of atomic orbitals and identify the roles of basis function and expansion coefficients. So let's see what the problem is. We are trying to describe a molecule that is made of electrons and nuclei. We already looked at the Born-Oppenheimer approximation. We saw that the nuclear kinetic energy can be treated separately. We saw that the nuclear-nuclear repulsion energy can be added as a constant, so it doesn't really affect the wave function, the electronic wave function. So what we care about here is the molecular electronic Hamiltonian. So we have the kinetic energy of all of the electrons here in blue, and then the electron-electron repulsion between all of the electrons, and then the electron nucleus attraction from each electron to each nucleus. Notice that I'm using capital letters to describe nuclei and I and J's to describe electrons. So this is the legend to interpret this Hamiltonian, and indeed the Rij is electron-electron distance, and Ria is the electron nucleus distance. All right. Now, to make things simpler, but not any approximation involved here, we just shift the system from the international system to atomic units. So mass of the electron is 1, charge of the electron is 1, and all of that fun stuff. So we can simplify this Hamiltonian into this one here. Nothing has changed, we just changed the reference system, so we have less constants to carry around. Now that we have that, we need to solve the Schrödinger equation. So we need to apply this electronic Hamiltonian to our wave function that in principle is a wave function of all of the electrons in the system. The nuclei really toss them on the side, separate that out with the Born-Oppenheimer approximation. That gives us the electronic part of the energy. Then we sum up the nuclear repulsion and we get the total energy. And that's it. So we need to figure out how can we write this psi here. So that is the next step. We can write the psi of all of the electrons as a product of mono-electron wave function. That is the same approach that we used when we looked at the helium atom. We wrote the wave function that we can write. It should be a wave function of both electrons at the same time as a product of electron 1 wave function and electron 2 wave function. We knew then that that was a very bad approximation already from the helium, and so it's going to be a very bad approximation here, but guess what? That's the best we can do. So we go ahead and we write this. But when we write this, which is a mean field approximation, we realize that there is a problem with that. We knew that already. It's not antisymmetric upon the exchange of the coordinates of two of the electrons. So how did we solve the problem there? We use the Slater determinant. How are we going to solve the problem here? Guess what? We're going to use the Slater determinant. And so we build molecular orbitals using the Slater determinant of spin orbitals. Let's refresh our memory. What are spin orbitals? They are the product of a spatial part. In the helium atom, it was just the 1s, 2p spatial part of the orbital times a spin part, which is alpha or beta. Here, we're going to see that the spatial part is going to be a little bit more complex than in the case of atoms, and we're going to form what we're going to call molecular orbitals, and we're going to see how we do that in a minute. But for the moment, spin orbitals for molecules are nothing else than what we saw for atoms. It's a product of a spatial and a spin part. And we need that so we can write our wave function as a Slater determinant of spin orbitals of all of these electrons, so that we can anti-symmetrize the wave function upon the exchange of two electrons. So as long as we keep that in the back of our mind, that we need to have this Slater determinant on our side to describe this property of the wave function, then we're good. We can then focus on these spatial orbitals. So now we focus on the spatial orbitals, how we can form these spatial orbitals. What form should these phi I of R, these molecular orbitals, take for describing a molecule? And so again, let's try to compare what we did with the helium atom. For the helium atom, when we were trying to describe our wave function, we wrote it as a linear combination of hydrogen-like orbitals, and we optimized these variational parameters so that they minimize the energy. So we wrote that helium atom wave function is a linear combination of basis functions. Guess what? We're going to do the same here for molecules. So we write our molecular orbitals. So this is the ith molecular orbital phi, which is a function of the coordinate of whatever electron we are putting it in there. And we're writing it as a linear combination of theta. What are these theta? They are atomic orbitals. What are these atomic orbitals? They are these guys here, the ones that we were using on the helium atom and so on and so forth. So they are atomic orbitals. So we write a molecular orbital as a linear combination of atomic orbitals, and we're going to give each atomic orbital 1s of atom A, 2s of atom A, 1s of atom B, 2s of atom B, 2px of atom B, and so on and so forth. We're going to give each one of these atomic orbitals a weight by changing this expansion coefficient. So we can treat this molecular orbital again with the goal to minimize the energy. And we sum all over all of the atomic orbitals that we have available. So you already realized that I'm not focused only on one atom when I build this molecular orbital. I sum over all of the atomic orbitals for all of the atoms in my molecule. What we've done here is a linear combination of atomic orbitals, LCAO. And so let's see an example of this. So suppose that we have a molecule made by 3 atoms, 1, 2, and 3. And we're going to put atomic orbital theta 1 on atom 1, looks like a 1s to me, and an atomic orbital theta 2 on atom 2, by the size that could be a 1s, a 2s, depends on how you look at it, and another one on theta 3, and that's what we done. We just did a linear combination of atomic orbitals, and so we formed phi 1 molecular orbital. Let's do it again by changing these atomic orbitals that we are summing. So let's do another linear combination of atomic orbital to form a different molecular orbital. I'll still put a 1s on atom 1, but this time on atom 2, maybe that was an oxygen, I'm going to put a 2p something, say 2px orbital. That looks like a 2p. And so then I'm going to put a 1s on this other atom, say that this is a hydrogen and that looks like maybe a water molecule. But I'm going to change the sign. I'm going to change this. How can I change the sign of the molecule, of the atomic orbital? By changing the sign of the expansion coefficient. So that's how we can form this linear combination of atomic orbital. These c mu I don't have to be positive. They can be positive and negative. So I can change the sign and mix these atomic orbital in the way that it's convenient. So we formed a different molecular orbital phi 2. And then we're going to put the electrons in these molecular orbitals. So to summarize what we have seen here, we have put mu that are indices of basis function theta mu, which again are atomic orbital. Better here, I should have used atomic orbitals here, theta mu, typically centered on atom A, 1, 2, and 3. So these mu's don't stay on just one atom. They span all of the atoms in your system. So M runs all over the atoms in your system. The next question is, how can we write these theta mu, these atomic orbital? Well, the simplest way to do it is just to use what are called Slater type orbitals, or STO, which are just S-like exponential decays, like we were looking at over here. Here for the helium atom, at some point we realized, oh, we can use many of them to better describe our orbital. The simplest case, we can use just one. It turns out that in reality, we still use many of these. So this theta is actually going to be a linear combination of basis function. And in computational chemistry, there are even more tricks that one can play to make these orbitals behave even better. But for the moment, we don't need to worry about what are these theta mu. They are just atomic orbitals that can be expressed as exponential decays for S-type orbitals. So there you have it. We have defined what a linear combination of atomic orbital is. We have seen how we can use it to form molecular orbitals. And we have taken a look at what these atomic orbitals that form this molecular orbital can look like.